Now I want to spend some time discussing decision making for similar exposure groups. And the common exposure assessment paradigm is that we prioritize agents and SEGs and make decisions using the following approaches listed in this order. We have been, as a profession, considering quantitative measurements as our gold standard, and that's sort of the most objective way of making decisions. And then the next approach is to use the professional judgment of the industrial hygienist. And the third one is modeling. And the size of the font refers to the degree to which these three approaches are being used. So, what is wrong with this paradigm? As we have discussed in previous lectures, collecting measurement data is not always practical and it's not feasible for economic reasons because it's very expensive to make measurements. And then in many cases, it may not be even possible. So, for example, there are a couple of scenarios we can discuss. There are many requirements that must be met prior to the introduction of a chemical agent into a workplace. For example, you need to have approval, hazard communication training, PPE and respirator selection, assessing engineering controls, process hazard reviews, and emergency planning. So these types of steps need to be in place and completed prior to the collection of any measurement data. So clearly in such cases, we will not have any monitoring data to make any decisions. And as I mentioned before, collecting measurements is resource intensive, and so it limits the number of scenarios that can be measured, and in many cases results in the evaluation of what is thought to be the highest exposure scenario or the worst case scenario. The time required to collect sufficient number of representative samples may be too long compared to the time period necessary to support the exposure control program. So it may not really be a feasible approach for that reason. It is also important to know who was not exposed or who had low exposures, as it is to know who had high exposures. So, for example, if you want to have a medical surveillance program in your organization, or if you are involved with an individual worker illness case, or illness clusters, or epidemiological studies, or toxic tort cases, in these cases, you need to not just be able to identify who was exposed to the highest, but who also had low exposures. So if you are conducting an epidemiological study, you need to be able to assess exposures for the low exposures or unexposed workers as well. And so we would not be spending money as an industrial hygienist monitoring office workers necessarily. So the next bullet is, in some cases, the numerical value of the OEL, analytical methods may not be available, or they may lack sufficient accuracy and precision. And finally, the most important part is that even if we make a few measurements, the quantitative exposure assessment may fail to correctly identify unacceptable exposures. And so this is one of the biggest limitations of an exposure assessment that is solely based on monitoring data. The AIHA model is based on the idea that it is going to lead to a decision. And so the focus on decisions drives exposure management. So each SEG must be judged as acceptable, unacceptable, or uncertain. And we make this judgment on the basis of comparing the exposure profile for the SEG and its accompanying uncertainty with the occupational exposure value or occupational exposure limit and the uncertainty in that value. Using the AIHA exposure risk management strategy, the goal here is to define exposures using all available information. So we first use qualitative methods and provide an initial assessment of the exposures for a particular SEG. And you may also use mathematical modeling to do this first pass of exposure assessment. And as I mentioned earlier, the next lecture we'll be looking at some of the tools for initial assessment. These are what I call rules of thumb. And then we collect monitoring data during the second, third, and so on passes, and we may validate our initial judgments or revise our initial judgments if they are wrong. So this is an iterative process where exposures are refined through each pass. So in my previous lectures, I've talked about different decision strategies, and we had arrived at a strategy based on looking at the 95th percentile of the exposure distribution. But people have developed other exposure assessment strategies or decision strategies as well. And here are some examples of such strategies. The first one is if all the measurements in a data set are below the exposure limit, then it's considered acceptable. Or if all the measurements in a data set are below 50% of the OEL, or what is called the action level, then it's considered acceptable. Or when the 95th percentile of the exposure distribution is below the OEL or the action limit, then we say it's acceptable. Or if the exposure metric falls into a desired exposure band, then it's considered acceptable. And we have spent a lot of time looking at the statistics of exposures and the 95th percentile and so on. And I'm going to spend a few more slides just to drive home the point that having few data points is not a sufficient basis for a good exposure assessment and frequently may lead to wrong decisions. So in this slide, I'm showing an exposure scenario where the OEL is 10 parts per million, and we have, for a particular SEG, a geometric standard deviation of 2.5 and an action limit, which is 50% of the OEL, so that's at 5 parts per million. In the first column on the left, we have the exceedance fraction. And so we have everything from 50% all the way down to 2%. And if you recall, we have decided that an exceedance fraction of greater than 5% is considered unacceptable. And so if we know the geometric standard deviation and the exceedance fraction, we can sort of back calculate what the geometric mean or GM is in the second column. We can calculate what the 95th percentile is in the third column, and the portion of the distribution that is less than the exposure limit in the last column. That is, of course, the non-exceedance fraction. And the next 5 columns represent the portion of time in percentage that all measurements of a data set with a size n will fall below the OEL. So, for example, if you have only one data point in your data set, then there is a 50% chance that it's going to be less than the OEL because the exceedance fraction is 0.5. If you have an exceedance fraction of 25, then with one data point, there is a 75% chance that it's going to be less than the OEL, and so on. But let's look at the other end of the size where we have a data set size of 5 measurements, n equal to 5. So the point I want to make here is that let's just focus on the exceedance fraction of 5% or 0.05. And we have made 5 measurements. And so we have a 77% chance that all 5 of the data points are going to be less than the OEL. And that means that we are just at the edge of acceptability at 5%. If we have n equal to 5 and we have a 59.1% chance that all measurements are below the OEL, that corresponds to an exceedance fraction of 0.1. So it's an unacceptable scenario, but 59.1% of the time, all 5 data points are less than the OEL. And so we cannot use a strategy where we say that if all 5 measurements are less than the OEL, then it's an acceptable scenario, because clearly it leads us to an unacceptable exceedance fraction of 10%. What if we use the action limit rather than the OEL to do the same thing as before? Again, we have reduced the problem somewhat, but even then, if we look at an exceedance fraction of 0.1 or 0.25, and we look at n equal to 5 measurements, we have almost a 17% chance that all measurements will fall below the action limit. So it's much less than when we looked at the occupational exposure limit, but using the action limit and just using the idea that all 5 measurements are less than the OEL or AL will lead to a better decision is not necessarily right. Let me show you another table. And here I'm showing this table where in the top part, highlighted in yellow, we have 5 columns. And below that, for each column, I have the average, the geometric mean, GST, and the 95th percentile listed. And you can see as we go from left to right, the 95th percentile increases. So for the first data set, the 95th percentile is 3.75. And for the last column, the 95th percentile is 60.8. So what do these 5 data sets below have in common? Each data set has only 5 measurements. Each data set came from the same exposure distribution. And so what this shows us is that there are 48 data sets of 5 samples each that were generated from an exposure distribution where the OEL is 10, the action limit is 5, and the exceedance fraction is 0.25. And so the individual data sets 95th percentile range from as low as 3.75 to as high as 60.9 parts per million. And out of the 48 data sets, 85% had a 95th percentile that was well above the exposure limit of 10 parts per million. And one of the 48 data sets had a 95th percentile below the 5 ppm action limit. So you can see that even though this is a clearly unacceptable scenario with an exceedance fraction of 25%, depending on which data set of 5 data points you happen to measure, you might arrive at very different decisions. So the previous slides were just to provide a caution that we should not blindly believe the results of a statistical analysis, especially if you have a very small number of data points, in this case, n equal to 5. We need to bring to bear our own professional judgment. Does the statistical analysis make sense? And is it consistent with your experience and with other comparable SEGs? And is it consistent with published information, such as the scientific literature or the NIOSH criteria documents, and so on? And then is the statistical analysis consistent with basic characterization information and with the expected performance of engineering controls? Are the results consistent with the rules of thumb, which we haven't discussed, but we will soon? And are the monitoring results consistent with mathematical modeling? So how does one fix this exposure assessment paradigm? What I would say is that we need to give comparable weight to quantitative measurements, but also to the results of mathematical, statistical, and deterministic models, the rules of thumb that have been developed, as well as industrial hygiene professional judgment.